Whoa, welcome guys. Okay, so in this video, I want to talk about basically mean and variance for common probability distribution. So subscribe to my channel, click the like button. Okay, so the idea is that I want to show a mean and variance for a common probability distribution. So there are I think 11 of them. So a Bernoulli binomial hypergeometric function, a negative binomial geometric distribution, Poisson, uniform, normal, exponential, gamma, chi-square, and Weibull. So I think up to Poisson, the first six of them are discrete distribution, and the rest the six of them are continuous. This is just using the brute force technique. So we just do the integration, do the summation. So there's no characteristic function, no Fourier transform, no Laplace transform. Okay, so yeah, and no other like real analysis or any special technique. Okay, so hopefully it will help you. So be sure to subscribe to my channel, and if you want to just see any one of these, I already leave the time tag below, so you can just check. I'll just first record. So the discrete variable, suppose x has a1 up to an value. Basically, it can go to infinity, right? So ai is just some real number, and ex is just px equals to ai, and then from sum of I. And the variance is defined to be this. Variance is just ex squared minus ex squared. Okay. For continuous, if you have the probability distribution p, then ex just x px dx, ex squared just x squared px dx, and the variance is just this. Okay, so let's first see the Bernoulli. Let's see the Bernoulli distribution. Okay, so x from 0, 1 mean p variance is p1 minus p. Okay, so Bernoulli has x can only be 0, 1, and for 0 it has probability 1 minus p. For 1 it has p, right? So ex just 0, 1 minus p plus 1 plus p, so it's p. Ex squared is just same, right? Just 0 square, 1 square, so it's still p. I written I should say, right? So it's p, yeah. So p minus p squared, right? P minus p squared is p1 minus p. So it's the same as this one. Okay, so a trivial guy. Okay, binomial expectation value are the very common. So I don't want to. I think this is the common derivation. So let's quickly see. So for easiest way, we will let q equals to 1 minus p. So x is k, and the probability n choose k, p, k, q, n minus k. So you start from here. And one important identity that we will use in the future is that is k and k equals n minus 1, k minus 1. This is very important. We will keep using this. So you just combine these two into this, and pull out np, and pull out this as this. You see, so you pull out one np, right, and then it becomes k minus 1, n minus 1, k minus. So these two terms will combine as another p plus q to the n minus 1, right? So it becomes np. Okay, so ex is np. Okay, and another proof is that the Bernoulli process. The binomial distribution is basically the sum of an independent Bernoulli process. So the expectation value is linear. So you just take the first answer p and times n, become np. Okay. And the variance is the proof is somehow the same, right? But it's a little bit complicated. So you just cut times k squared, and then try to write it as kn, and then try to become this. You can use this, and then you expand it and use again. Okay, so it's a little bit complicated. You can just check this. You can just click the stop button and check the derivation. Okay, and use the same binomial, and then you get np 1 minus p. This is pretty standard, and we will see the same technique in the future. So I will leave the detail. Okay. So hypergeometric distribution is a lot probably the difficult one. Okay, so it's look like this. And the main idea for the hypergeometric distribution is we need to list among the Van der Waals identity. Okay, so if you don't know about the van der Waals identities, you can see my videos. There's a two proof for this combinatorial identity. This is easy. The proof is easy, right? Basically, you have n plus n r and k r minus k m n. So it seems like you can separate this m and n and run over all the possible k and r minus k. So this is the easy way to remember this identity. Okay, and this is on for my this is I write a derivation. So let's say this is your expectation probability distribution. So you times x, right? Because x is what your random variable can be. So you times x, kx, n minus k, n minus x, and n larger than choose n. Right. So you see this x is chosen to be when these two binomial coefficients are well defined. Okay. So x from 0, you choose, then this x k is become k minus 1, x minus 1, n minus k, n minus x, n minus n. Okay, so you pull out k, become k capital N, choose n, and k minus 1, x minus 1, n minus k, n minus x. Okay, so if you see carefully, it seems like if you add these two, right? You add these two, you get n minus n plus. You get n minus 1 and let's say small n minus 1. If you use the van der Waals identity, okay? So this is x minus n minus x. Okay, so you can change this x0 to 1, right? Because x0 is ill-defined. I mean, at least for here, right? If you put x equals 0, then this turns 0. So you can change x to 1 and use the van der Waals identity. So it becomes capital N minus 1, small n minus 1. And by definition, you just write down all the definition of binomial coefficient. Then you see these two terms cancel, and this is survive. So it becomes capital N and the kn. Okay. So yeah, so this is the expectation value. I think it's here. It's the same as here. Okay. Basically, the calculation is not difficult, right? But a little bit lengthy. Okay. Variance is very lengthy. So, yeah. So I will. I already write down detail, right? So you can click the start button and copy if you want to write your homework. Okay. But the idea, but let me quickly mention the idea. So the idea is that you do the x squared, right? Here x squared, and then you write x squared as x minus 1 and x. Okay, so x kx is the same, and x minus 1 kx is become this. So you separate into two terms. Okay, and the same trick, right? Same trick, you can use this. Oh, sorry. Okay. So I missed something. Let me just write the important. Sorry, I missed something. So let me just I missed something important. So this is k. There's a k minus 1. Yeah. Okay. Otherwise it's stupid. Okay. So this is correct. Okay, so for this term, you change it to this term, okay? And for this term, it's the same as what we already did, change it to these terms. Okay, so and then it's easy to see that this is another van der Waals identity. This is another van der. So you use the van der Waals identity twice. Okay, so these two product of binomial coefficient become this, and then these two binomial coefficient become this. Okay, so you have these two. And you just brute force do, right? Then this term is original one, right? Nk divided by n, and this is k minus 1 times, I should say, times n minus 1 divided by capital N minus 1. Okay. So this is remember this is ex squared, right? We need to calculate variance, so we need to use ex squared minus ex squared. Okay. So you get this. By the way, this capital N is capital N. So I use Mathematica to help us. So this is Mathematica. Just for fun, right? So this is the ex squared. This is our ex squared. Okay, so you can check by the you can check and do the for simplify and check with the textbook answer, and then you will see they are the same. Okay, so that means our calculation is correct. Our calculation correct. Okay, so let's see the so-called negative binomial. In this video I will not talk about the meaning of negative binomial. Okay, so I will just talk about the expectation value and the variance. So as I said, right, since we do not use like the other theorem, like this memory property, characteristic function, Laplace transform, Fourier transform, and other real analysis technique. So for us, it's a little bit difficult to derive all the. So that's why we have the somehow like the lengthy derivation, because we will not use like other like the fancy technique. Actually, their techniques not fancy, right? But it's not necessary to prove this EY and prove its expectation and value and the variance. Okay, so this is the prob distribution. I think everyone knows about x r plus 1 and this. Okay. Usually to make the derivation simple, one can just use x minus r as our y, just for fun, right? X minus r as y. So so we get y equals to y become this. Okay, and the EY just see the derivation. Okay, the key trick is the same, right? You just pull out this one term as this, and then you combine this as another binomial distribution, and it become r 1 minus p divided by p. So it's the same technique as we use. Basically, there's just few identities that you can use in to compute this so-called binomial coefficient. Okay, and but remember, we will first derive EY and EY squared, and then we need to change back as EX and EX squared. Okay, and the change is not nonlinear. For the expectation value is linear, but for the EY squared is nonlinear. Okay, and you can do the EY squared, so there's a Y squared term here, and the same trick you write Y squared as Y squared minus Y and plus Y, right? So this is the same technique as we did. Finally, you get R plus 1 minus P squared plus EY. Okay, so it's the same trick. It's exactly the same trick as when you encounter something x squared, you just write it as x squared minus x plus x. So in this case, it's y squared minus y plus y. Okay. 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 So let's see the results. Okay. So we know that the y is x minus r, right? So EY is EX minus r. So it's r 1 minus pp. You see EY is here. Equals EX minus r. So EX is r times 1 minus p plus p plus 1. So pp cancel, is r minus divided by p. So if you see our correct answer, people like to see is written as k minus p, right? But in our case, k is r. So it's r divided by t. Sorry, r divided by p. Okay, and also y is x minus r. So this is an easy exercise that you should do, right? Y is x minus r. So y squared is x squared minus 2xr plus r squared. So EY squared is ex squared plus 2r ex plus r squared, right? And we already know this. We already know this EY squared is here, right? And then we get the EY, and then we get ex squared plus minus 2r divided by p at r plus r squared. So all the brute force calculations lengthy, but you get e squared is here, and the variance is e squared minus ex squared. So finally, you get variance is this. Okay, and you have 4 terms, right? You have 5 terms, right? But if you brute force do it, you get r 1 minus p divided by p squared. If you patient enough, okay. And I just want to say that if you use Mathematica and follow all the derivation, then finally you force simplify, you get r 1 minus p squared. So nice, right? That means our calculations are correct. Okay, the next is so-called geometric distribution. So f is p 1 minus p x power x x to the minus 1 x from 1 to 3, 4, 5. Okay, so if you see if you sum of all f, you get 1, right? By definition, this is just this is geometric series. Okay, so ex you just times p, right? You just become, so it becomes p times x, right? So it become p plus 2p 1 minus p plus 3p 1 minus p squared plus 4p 1 minus p cubed, and you can pull out 1p, p 1 plus 2 1 minus p 3 plus 3 times 1 minus p squared 4 1 minus p cubed. So we know that k from 0 to infinity x to k is 1 divided by 1 minus x when x is less than 0. So you get 1 plus x squared become 1 divided by 1 minus x. So you divide x. So you differentiate x, right? You get another identity, 1 plus 2x plus 3x squared, equals to 1 divided by 1 minus x squared. Okay. And you have 4 terms, right? You have 4 terms, but if you brute force do it, you get r 1 minus p divided by 1 minus x. So you divide x. You also so you differentiate x, right? You get another identity, 1 plus 2x plus 3x squared, okay. So it's very nice that we just use this identity. So in this case, if we let x equals to 1 minus p, we get this, right? So this guy is this. So it's p divided by 1 minus b squared. So we get 1 over p. Okay. So for geometrical, the expectation value is 1 over p. Let's see. It's the same as for our table. Right, table is 1 over p. Yeah, doing a lot of video is difficult, but yeah, I just want to summarize this for future, like people will keep asking me the derivation. So I built a video to solve all these stupid things. Okay. So ex squared is just px squared 1 minus p to x minus 1. So you write down, you get p 1 plus 4x 9x squared 16x to the cube. So this is yeah. So you get this, right? You get this. If you start from our previous case, you times right, this this equality comes from because you times x for this equality, and you do the differentiation again. You get 1 plus 4x plus 9 squared, right? So this term looks as exactly the same as this term. Okay, so then you get this, and then you pull out you just put x equals to 1 minus p. So if you see start from here, and then you do the differentiation, you get these identities, and then you let x equals to 1 minus p, right? And then you will get this term, and this. By the way, there's a p here, cut by, yeah, there's a p here. Okay. So p, so this is your ex squared, right? 2p minus p squared, p to the 4p. So you just put x equals to 1 minus p, okay, and the times p, okay. And the variance is this minus original 1 minus p squared. So this is variance, right? And the calculation, you get the pp cancel, you get p squared 2 minus p minus 1, you get 1 minus p squared. Okay, so I write all the notes because I don't want to waste your guys' time. Okay. Finally is the final our lovely, and basically like 90% of the textbook like to ask or 90% of exam or probability exam like to ask a Poisson distribution. The reason is that which is somehow a little bit non-intuitive. Okay, so the Poisson distribution says that x can be your variable can choose 0, 1, 2, 3 up to right infinity. So pxn is like exponential lambda t to the power n factorial. So like all the textbook or Wikipedia, usually people will let lambda t to be another factor like lambda tilde. Okay, so I use lambda tilde just for fun. Okay, so this is p. And the expectation value, right, by definition should be lambda tilde. So it's by definition, right? But do a derivation is also simple. You just pull out one lambda tilde, and because there's n, right? So n changes into n minus 1 factorial. So you pull out one lambda tilde, and the rest becomes still the exponential factor. So you get exponential negative lambda tilde times exponential lambda tilde times lambda tilde. You get lambda tilde. Okay, so it's like a tire expansion and your easy calculus. Okay, and ex squared is the same, right? You get n squared, right? So the same trick, every time you see n squared in the probability, you should write it as n squared minus n plus n, right? This is already happened thousands of times. Okay. So you start from here and you expand these two terms. So the first term gives you like n factorial, 1 minus 1 factorial, and this is n minus 1 factorial. Okay. So you get lambda tilde squared plus lambda, and then your variance is lambda tilde squared plus lambda tilde minus lambda tilde squared, and then you get lambda tilde. Okay, lambda t. Okay, so if you're like if you go back to our table, one is lambda t, and the mean and variance are both lambda t. Okay, so very easy. Actually, it's fun exercise. You do it by yourself and do not see my calculation. But yeah, so I just want to help you guys. Okay, so after this, let's go to the so-called continuous. So in the continuous region, that the probability distribution become a real continuous function defined on some real interval, right? So after you have this, then all you need to do is just write down the x probability px and do the calculation, do the integral. So in the previous discrete variable, we like to use like many summation, many strange detail. Sorry, this is fine. So many strange clever identity, right? But for the continuous, nothing we can do, right? Oh, the only thing we can do is like test our integration idea in the calculus, maybe integration by power change of variable. Okay, so it's a little bit different. Okay, so let's quickly see the stupid example. So stupid example is uniform, right? Because your function defined on a continuous variable, your continuous function defined on some real interval, then what else it can be, right? So the easiest one is the uniform f1 minus b minus a x from ab. So expectation value x dx b minus a is a half x squared divided by 2, and you pull out ba. Okay, so I miss a line, right? This should be a and b. Become this. Okay, expectation value also straightforward. You get x cubed divided by 3, and this should be the upper limit is b, the lower limit a. Okay, so I should add this line. Okay, so let me just add it. Actually, doing the YouTube video for me is like the very happy things, because I can meet you guys online, and you guys can see through me. Okay. I mean, if my video got a lot of subscribers, I can broadcast and say something about my story, but it's not important. Okay. So you get b squared plus a squared plus ab plus a squared. Okay. And your variance just straightforward, right? You just write down your ex squared minus ex squared, and you expand it, and you get this. Okay. 1 over 12 b minus a squared. This is also like the textbook exercise. Yeah, calculation is it's basically easy. I already write down details. Okay, next I should skip. But the next is so-called uniform, so-called normal distribution, which is the number one distribution in the probability distribution. So somehow, like for some people, it says that if you know. Basically, if you can forget all the distribution, but remember normal distribution. Okay. And in the popular science or some popular articles, or popular media, somehow like people like to say. Okay, so f is, yeah, I mean I don't want to say. So it's just very standard, and ex is just very standard, right? Ex you just use x minus mu as y, and you do all the calculation. The key idea, all you need to remember is this. So we will use like the gamma function in the after video. But this is so-called Gauss integral. So if you don't know, you should go to my YouTube channel and see proof for it. So I will not prove here. This is like the very common integral. Okay. So you can go to my video and type the gamma function. Actually, all these type of integral can be solved by the gamma function. Okay. So the expectation is mu. And the calculation is here, and you can see ex squared is here. Ex squared I need to use another, but this is also the derivation of the gamma function. I will leave the gamma function identity if you are interested. Basically, I prove many relevant video, many integral video as this formula, so you should check it if you don't know. Okay, so variance will be sigma squared. Okay, as what we expect. Exponential also a gamma function technique. But for exponential, probably we need to use, right? This is the gamma function definition. 0 to infinity tn exponential a t dt will be n factorial divided by a to n plus 1. Okay, so our probability distribution is 1 divided by beta exponential negative x divided by beta. Right, x from 0 to infinity, right? And the first one is ex. Ex is here. Okay, so ex is 1 over beta 1 factorial 1 minus beta squared, right? If you use this formula, a is 1 over beta. So it's beta times beta squared beta. Okay, so 1 over beta times beta squared, so it's beta. Okay, and the ex squared is 1 over beta x squared exponential negative x divided by beta dx. So it's 1 over minus 1 divided by beta to factorial 1 divided by beta to the cube. So variance is that, so ex squared is 2 beta squared minus beta squared is beta squared. Okay. So exponential, all the higher moment of exponential distribution can be directly seen by the gamma function. So as I said, if you don't know the gamma function, I will leave the link below, and you can check my gamma function tutorial. There are 4 of them, and the proof may be 80% of gamma function identity you need to know. Okay, And this is the so-called gamma distribution. I already write down a gamma function. Okay, so I write down here for your main purpose. Okay, so ex is the same. Ex is the expectation value just times x. Alpha become this. And you see this is exactly the definition of this. You just use this. And the definition of gamma function to change your variable. So you can just, I already write down details. So you start from here, and then you get this is alpha plus 1. And then you get this, and then you get this, alpha beta. And the ex squared is almost the same as ex, right? And the only difference is just change alpha plus 1 to be alpha plus 2 because there's x squared here. And you use this formula. This formula just come from this gamma function and do the so-called change of variable. So you get alpha plus 1 beta squared. So remember that remember that gamma alpha plus 1 is alpha gamma alpha, right? You can view the gamma alpha plus 1 is just alpha factorial. Okay, so your variance will be alpha beta squared because you use alpha plus 1 beta squared minus alpha squared beta squared. So the first term cancelled, the rest is this. Okay, and the chi-square derivation also use the gamma function. So basically all the continuous variable like the up to except for normal, except for uniform, normal, exponential, gamma, chi-square, Weibull use all the technique of gamma function. So the gamma function is very important in the probability distribution. If you don't know that, you should go to my video and check. Okay, and I leave the chi-square. Chi-square, right? You just follow the same calculation. Your xv is this, right? And then you do the ex, you times x here, and then you pull out this. So this xv divided by 2 exponential x divided by 2 dx is from 0 to infinity is this formula. Okay, so you should use alpha as v divided by 2 plus 1, so this, and pull out the coefficient to a v divided by 2 plus 1. And easy calculation to see this is just v. Okay, and the ex squared is the same. Okay, so the final you can prove the variance is 2v. There's only one trick, this trick. Okay, so you can check my gamma function video. Okay, and the Weibull is this one. Okay, so the calculation is very lengthy, but the same trick, gamma function. Just first let these to be y and change this x to. So let's say maybe we check ex is x f dx from 0 to infinity. So it's alpha beta 0 to infinity x beta exponential minus x alpha x beta dx. Okay, and then you change this as y, and then this is your x, and the dx. Okay, so see I think you can just click the start button and copy and read my calculation line by line, and you will understand. Oh. Straightforward. Okay, so alpha beta 0 to infinity y divided by alpha, this one, and you see alpha beta will cancel, right? Finally you get alpha 1 minus 1 divided by beta and the rest. So this you get y 1 over beta exponential negative y dy. So by definition this is the gamma function definition. Alpha minus 1 exponential x, you just change x to y, then you get the gamma 1 divided by beta plus 1. Okay, so this is your ex. Ex squared, I think you guys can check. I don't want to waste your time, but you can just check the derivation, and all the rest are in the video. Okay, and I will leave this PowerPoint as you can download and go back to your own reference. And if you see there's some mistake, just comment in my video. Okay. So finally, hope you guys actually subscribe to my channel, and yeah. So ex squared just. Finally you get this, right? And the variance just use this minus this. And it's very it's also amazing that this alpha minus 2 divided by theta can be pulled out. Okay, and you get 1 gamma minus gamma squared. Okay, so it's very interesting that we use the gamma function technique and some easy trick of binomial identity, and we solve this 10. So all the details are in all the detailed derivation are in this PowerPoint. And most of them I explained, and a little bit of them I don't, right? But the key idea is this gamma function. So check out my gamma function video, and I will see you guys in next videos.